Sorry.
All right. So where were we? So last time, we got as far as an infinity. So we basically proved that the supremum over theta in this WQK, WQK is this set of theta equal to A over Q plus beta, where Q is of size Q, A and Q are co-prime, and beta is of order K over N. And we show that the supremum of the Fourier transform, this exponential sum, is bounded by, well, there was a trivial bound n to the 2 delta. There was a bound of something like n to the 2 times 1 minus delta, so something that's going to be small if delta is close to 1. And then what we want is a factor of k times q. And that was enough to get a bound. So again, I'm thinking of kappa. Yep, my favorite picture. K is n to the kappa, q is n to the alpha. Alpha goes up to a half, kappa goes up to a half. Here's the major arcs at some kappa 0, alpha 0.
Which the analysis works.
So the analysis, exactly, when you put it into this integral, when we look at the integral over WQK of r hat squared, this is bounded by just the L infinity bound. This is the L infinity bound in this region. So we get n to the 4 delta plus some crap. I get to divide by k squared q squared. And the length of this sum is q squared times k over n. And so the q's are gone. The k, one of the k's is gone, and I've saved a k. Okay, so this is little o of n to the 4 delta minus 1 with this factor k. So as long as k0 is at least a little bit something, we win.
Okay. I don't.
This
K0, how does K0 work again?
We haven't talked about that. We haven't talked about that at all.
Oh, it's like a parameter you'll specify at some point.
In the major arcs, yes. So we have to close the gap between how far we can go in the major arcs.
Okay.
And there's going to be some kappa 0 where as long as beta is less than k0 over n, and q is less than q0, which q0 is n to the alpha 0. Then we can get good approximation to what's going on, and we can estimate everything, and we'll get some singular series times n to the 2 delta minus 1.
Okay. And can you mention the heuristic again of like right, this inequality that you wrote down? You're saying like,
here
further down, right? Like
this
that,
one?
Yeah, that inequality, right? You're saying like, oh, if k is at least this certain amount.
Yeah, we have to beat what we need for the density 1 theorem is that the sum of the error terms squared over n is little o of what the main term is on average. So the individual main terms are n to the 2 delta. So if I square that, I have n to the 4 delta minus, so in other words, n to the 2 delta over n is the main term. So the major arcs will tell us that the main term for a given number n is at least some singular series. Let's pretend that singular series is 1 times n to the 2 delta minus 1 plus some errors that are acceptable. So let's just be crude. Okay, this is the correct multiplicity. This is what we think the multiplicity should be
For major arcs.
For the major arcs. That'll give us a main term. So the minor arcs, which are also the integral over the minor arcs of r hat squared, and that needs to be little o. We need this to be little o of this thing squared, which is n to the 4 delta minus 2 on average. So times n, which is n to the 4 delta minus 1.
Then you're saying over here we have n to the 4 delta
minus 1, and now we win.
You're going to make kappa 0 depend somehow on n in such a way that then this will be little
That's right.
o.
That's right. So we've successfully handled the minor arcs in this range.
With making kappa depend appropriately, however
Yes.
subtly convenient.
Exactly. And that'll also determine how close delta can be to 1 so that we can
And then
allow for
what-
this.
What kappa is controlling is what again in our,
Kappa is n to the kappa is k,
K, and then K.
and
is
k over n is how close your fraction is to, your theta is to the fraction
those
a over b.
peaks that we had. Like,
It's the width of the peaks.
it's the width of the peak. So you're saying that if we have a wide enough, if we have wide enough tolerance, then we handle that. case.
If we're far enough away, if we have a fraction, so let me draw this picture again with, something like this, right? Whatever it is. So the major arcs are going to catch some width kappa 0
Right.
around some fractions with denominators that are small.
Yeah.
The minor arcs, we are at least some distance kappa over n,
Mhm.
we're some distance kappa over n away from a fraction which may be small or may be large. So if we're near a fraction, but if we're centered at a fraction with small denominator, at least we're some distance away from it, then we expect cancellation. Or if we're near a fraction with large denominator and we have, so that's over here. Over here is large denominator and we're some distance away from it. But we might have very small denominator and we're some distance away from it. We still get cancellation.
You're saying here we're still in a minor arc,
Yes,
but
we're getting cancellation.
kappa is big enough so that like this will work.
Yes,
And then now we have to handle a case where like kappa is small, yet we're not like in a major arc.
now we're very near a fraction. What happens if we're very near a fraction? So kappa is small, but the denominator of that fraction is large.
Okay, we're near a fraction and the denominator is
But the
large.
denominator is large. So this fraction is a over q, but q is large.
And we're near a fraction or denominator is small, then we're in the major.
Then we're in the
arcs
major arcs.
case.
We're going to do a completely different analysis for this.
Okay.
You shouldn't be able to show it small.
There is no cancellation, right? Instead of cancellation, what we'll do is we'll catch main contributions.
And then alpha here is controlling
The size of q
the size of q, and then q
is the denominator.
is the denominator. Okay. Yeah, I'm just like
Yep.
putting the parameters.
We got to load this all in every time. Yep. Okay, so
Question.
Nick, you want to say something?
I have a question.
Please.
So last time when we were doing this, we changed our R sub n
Yes.
function. Why was that allowed?
So we changed the R sub n function to be bilinear form, n in gamma x, gamma 1 in gamma x, gamma 2 in gamma y. We introduced parameters x and y, whose product is n, so that we still have the right number of, the number of things here is x to the 2 delta, the number of things here is y to the 2 delta. Their product, so this is e to the 2 pi I theta v gamma 1, gamma 2 v.
It was next question.
Nick's question was, we changed Rn theta from the original Rn theta to
Oh, yeah,
this.
from the original one. Yeah.
Why is that allowed? We've changed the multiplicity. We've changed this is the Fourier transform. We've changed the meaning of the multiplicity function. Now we want to know how often n occurs in the 1, 1 entry. V is E1, V is 1, 0, where we have a product of, so gamma 1 is in this semigroup, gamma 2 is in the semigroup, the product is in the semigroup. So anything that occurs here will still occur in the original semigroup, just with different multiplicity. We don't care about the exact
As long as it
multiplicity.
gets represented.
As long as it gets represented, we're happy.
It's not like an identity.
It's not an identity, yeah. It's not a, this is the multiplicity. It's just, this is a lower bound. We just want to know when the multiplicity is not 0.
And right, you just want this little O thing to work so that like you get anything.
Right.
Literally anything.
Okay, and changing the multiplicity won't change how much cancellation we can get from this function, or how much cancellation this function has.
It will allow us to capture the cancellation. If we don't change the multiplicity, I don't know how to get cancellation. I don't know how to get started with Cauchy-Schwarz without creating bilinear forms.
Okay, maybe my question is, are we going to be using this new Rn theta for the rest of the analysis as well?
Yes, in fact, we'll be changing it yet again.
Oh, okay. It just feels like we're doing major arcs with one function, and now we're estimating error using a different function, but now the error of this other function might
So
be
the
smaller
major
than the
arcs,
error of the.
you're absolutely right. The major arcs has to be done with whatever function we come up with in the end, which is
Okay.
the function that we can control the minor arcs with. So we find the function with which we can control the minor arcs, then we go back and do the major arcs for that function, not for the original function.
Okay, that was my concern,
Yep.
and I'm quite okay with this then.
Okay, great.
Thank you.
Yep.
Then, are you presenting this in the order in which you prove things when you were doing it? Like you.
Pretty much. Yeah, I'm trying to give you, I mean, I was debating between showing you what happens when you try the first refinement. We're here to learn, right? You don't want just the answer, how it goes in the end. You want to know how you find these things. Okay, so let's do, so in that case, let me go a little faster if I can. Let's try a first refinement. First refinement.
What you're saying will fail, right? Like
This,
it
it
was
turns out, will fail, but let's
it's-
find out why.
But it's the
it's-
first thing you would have tried.
It's the first thing you would try, yeah. Okay, so again, this integral is really an integral over beta. This integral W is really an integral over beta in this range, and then a sum over Q in this range, and then a sum over A mod Q co-prime of Rn hat of theta squared. So what I'm going to do is not square it. I'll pull out the supremum that we already established as a separate parameter. Okay, so it would be squared, but I'm pulling out an L infinity. And then getting a first refinement is try to get cancellation in this sum. A second refinement is to try to get a cancellation in both the A and the Q.
Looking at them together.
Yes, I'm going to look at them together and try to get cancellation. Okay, so let's go to the first refinement. So this.
It's possible to the third refinement. And then you
Yes,
looking
and
at the
indeed this
integrals
is-
together.
Yep, and indeed this is what people do
Oh.
to get better values of delta,
Interesting.
is to start cutting this up.
Look at everything all together.
Yep.
Wow.
And in a variety of ways. So you can fix the A's and sum over the Q's that are co-prime to the A and so on. There's all kinds of tricks one can play. All right, so we have a sum A mod Q. Now I have this absolute value. First thing I have to do is get rid of the absolute value. So for every Q is fixed and beta is fixed. So fix Q and fix beta. For every fixed beta in Q, this thing, Rn hat theta, which is really a function of A, has some sign, has some argument. So I'm going to put that sign as zeta A. So this is just something of absolute value 1 times Rn hat theta. And the Rn hat theta is this whole thing. So I have a sum over gamma 1 in gamma in a ball of size X, a sum of gamma 2 and gamma in a ball of size Y. Hopefully you're okay with this notation. Saves me a little bit of writing. E to the 2 pi I.
There aren't absolute values on this Rn hat theta.
There are, and what I'm doing is I'm catching those that absolute value depends only on A. Once I fix Q and beta.
Oh, then you'll be able to.
Then I'll be able to
Oh, so
reverse
that's
order.
capturing like
The modulus,
minus or
it's exactly the modulus of, this is equal to, I mean, if you want me to spell it out, it's Rn hat theta, where theta is A over Q plus beta, divided by the norm of Rn theta. So it's exactly the sign, or maybe the bar of the sign.
You're probably gonna not use anything about.
I'm not going to use anything about this. They're going to get Cauchy-Schwarz out in a second. Yep.
You're too complicated.
Yep. I'm not going to try to get any cancellation out of this. What I will get, I'm going to hit things, I'm going to hit Cauchy-Schwarz in the gamma 1 variable, as before. Okay, so I have V gamma 1, gamma 2, V. Okay, that's our sum. Now, what do we need? Let's get our bearings. What do we need about this sum? So what we already know is the length of this thing. The length of this thing is K over N, Q, And we have this supremum bound. The supremum bound is n to the 2 delta over k cubed. That's what we proved last time, if you recall. N to the 2 delta, or I'm ignoring this, over k cubed, times this sum over A and then R hat. Okay, times the first Kloosterman refinement. So the Q's are gone, the K's are gone. The trivial bound on this is Q times n to the 2 delta. So what I need to save, I have my n to the 4 delta minus 1. And what I need to save is a little bit more than this Q. Need to save Q to the 1 plus. Okay. So that's just to get our bearings. All right, let's do Cauchy-Schwarz in the gamma 1 variable. So I have a sum over gamma 1 in gamma of 1 squared to the 1/2 times a sum over gamma 1 in gamma of everything else squared. So A mod Q and gamma 2 in gamma Y, E of this stuff, norm squared, all to the 1/2. This is the only place where I'm going to get cancellation. Because I squared, every time you apply Cauchy-Schwarz, you double how much you have to save. So now I have to save not Q to the 1, but I need to save Q squared. That's already trouble. The length of this sum is Q, the original sum. I have this gamma Y. Maybe the Y will help me. So now I need to save from the inside. I need to save Q squared plus a little bit more. Because I'm going to take a square root.
So you're saying the left term is contributing what? The leftmost, the sum of the 1?
This is just this is going to give us x to the 2 delta to the 1/2. So it's going to give us an x to the delta.
No.
It's there's nothing to save from this. The savings needs to come here.
But are we worried about that? Thanks to the 3 delta.
It's a loss, but it's not. It's something where we're just going to pay that price to start the process. Okay, so this is just to get going. The fee for admission is to just lose. There's nothing we're going to save on this. We are going to save on that sum here. Okay, so there's an x to the 2 delta to the 1/2, so I get an x to the delta. Okay, this summation. So let me put the 1/2.
That's X. Gamma 1 and gamma X. The second time.
Gamma x, yes. Again, what I'm going to do is write this as gamma 1 transpose V times gamma 2V. Gamma 1 transpose V is some vector in Z2. And I'm going to stick in, so I'll take a Y in Z2, and I'll stick in my smooth function of size X. So this isn't just an upper bound for all of these. And again, I'm crucially using that the rows or columns, whatever this is, are unique. There are no parabolic elements in this semigroup.
And then also, we do the smoothing thing because of the Poisson summation.
Yes, we want to apply Poisson summation, and this thing will have support the Fourier transform. Let me remind you, the Fourier
type function or whatever.
Yes, exactly. The support of the Fourier transform will be contained in -1. Okay, and this is non-negative.
Is this like a standard example? I've never seen this type stuff.
Yeah, it's completely standard in this business when you want to smooth something.
Interesting.
Okay, so we have a non-negative function. It's at least 1 on some region. That's not really what I care about. I only care about that in order to replace this thing that I don't know anything about by nice abelian harmonic analysis at a loss.
Yeah, the power.
At a power loss, because it's going to be, there's x squared terms here instead of x to the 2 delta. So now I need delta to be near 1. Okay. And then there's this norm squared. Can I open up the norm squared already? Should I do it in 2 stages?
I'll open it up.
Okay, let's open it up.
It's only the first refinement.
Right. So let me write it here, and then I'll use the magic of the computer. So I have A and A prime, both mod Q. And then I have a gamma 2 and a gamma 2 prime, both in gamma y. And then in the inside, and I also have, let's not forget our zetas. There's a zeta A. So there's a zeta A prime bar, if you really care. And then I'll have this sum. So I'll make room, and then I'll put in what I have, e to the 2 pi I. I have a theta and a theta prime now. So I have a theta y inner product gamma 2b minus theta prime y gamma 2 prime v. Okay. And now let's do a little magic, which is to grab all of this. Oops, a little too magical.
Whoa.
What the hell? Oh my God, I can't undo this. Okay, delete.
Magic got strange.
Okay. So this is something you can't do so well on a blackboard. All right. So all I've done is I've reordered which one goes where. So I stuck in this function in place of this, and then I interchanged the orders. Now I'm going to put absolute values here.
Goodbye, Zetas.
Goodbye, zetas. Nice knowing you. All right, what are we doing on the y sum? Poisson summation. So the y sum is going to be Poisson summation, sum over k and z2. We did this already, so let me go a little bit faster. So this upsilon of y over x, e to the 2 pi I. Let's clean this up a little bit. The theta, I'm going to attach to the gammas. So I have an inner product y with theta gamma 2v minus theta prime gamma 2v times the Fourier transform, e to the minus k dot y dy. Okay, and the only thing I'm going to do is make a change of variables. Y goes to y over x, y times x. So that kills that.
Oh,
puts-
yeah. I had a small question about that. Why
Yes.
does that bring out an x to the power 2 factor?
So what I'm really doing is y is y1, y2, and I'm making change of variables. Y1 goes to y1x, and y2 goes to y2x.
And what the Jacobian is
Is gonna be x
pull
squared.
out X squared.
There's an x from each of them.
Many shares that come from the Jacobian, not somewhere else.
Exactly, Jacobian. So I get an x here, whoops, here, and I get an x there. So again, this is nothing but the Fourier transform at where? At x times theta gamma 2 minus theta prime gamma 2 v2. That's a element of
This
R2
would be some sort of cinch.
minus, yes, minus k. So I'm grouping the x over there. And because of the support of the Fourier transform, this is non-zero. This is non-zero. Well, not it. I mean, I didn't say that it's exactly the support. The support is contained. In order for this to be non-zero, I need that the distance to the nearest integer of theta y2 minus theta prime gamma 2 v exactly is at most 1 over x, exactly as we saw last time. And there's only one value of k for which that can happen.
Right.
So that sum is gone. Sorry? At most one.
At most.
Does at most one.
May not even happen. Right?
Exactly.
Like if you're somewhere in the middle of some like lattice points or whatever.
Exactly.
Okay.
All right, now let's do exactly what we did before. Let's write instead of, so before we put absolute values, let's look at a over q gamma 2v minus a prime over q. Same q, the q was fixed, gamma 2 prime v.
Just to be clear, this was the analysis that did work for like our big kappas
Yep.
or whatever. right?
Exactly.
And this is, however, now this is gonna fail for
Well, we're just repeating it to see what will happen.
okay, cool.
Okay, so this is theta gamma 2v minus theta prime gamma 2v, and then of course plus the betas or minus the betas, minus beta gamma 2v minus, there's no beta prime, this is the same beta, gamma 2 prime v.
So really what happened in the other case, the first refinement was enough.
The
For
0th
the-
refinement,
The 0th refinement just worked.
just the L infinity bound, worked if K was large, if kappa was large.
Okay, and then we just have to go through the refinements to like improve anything.
Yep.
Like, okay.
So now let's take the distance to the nearest integers of all of these things. Well, this I'll just bound by the actual distance. We already said that this in this range is at most 1 over x. Beta is k over n. This thing is of size y. Gamma 2 and gamma 2 prime are of size y. Beta is of size k over n. So actually y over n is 1 over x. So I have a 1 over x and a k over x. So this is at most k over x, just to simplify things. Now this is of size, if non-zero, so if the distance to the nearest integer is not 0, then it's at least 1 over q, because it's a bunch of integers with a fraction 1 over q. And q is at least 1 over big Q. And x was n to the 1/2. Remember, qk is at most n to the 1/2, which is x. And so k over x, this is too small to fit this kind of a distance from 0. So exactly as before, we get that a gamma 2 is congruent to a prime gamma 2 prime mod q.
And the reason,
Really only on v times v, but times v determines it anyway.
and this lattice distance business, we're able to apply it because we did the Poisson summation, or
Well, the Poisson summation got us into the position of the distance to the nearest integer of this difference being at most 1 over x. And then we remember what theta is. It's a over q, and theta prime is a prime over q plus beta.
yeah, I guess.
With
I was
the
just
same
wondering,
betas.
like, what was the extra information we got from the Poisson? Why not do it directly through the un-Poisson version?
So these are exponential sums. And Poisson summation is great at multiplying by an exponential sum into the value of the Fourier transform. And we control the support of the Fourier transform. So it's saying we're going to get cancellation in these sums. It's capturing the spinning. We catch spinning as long as we do have cancellation. In fact, the cancellation is total as long as this distance is, unless this thing is very close to 0. This very close to an integer vector. Okay, that's the beauty of smoothing. Think about what we did. We have a sum over all of y in Z2 of some function times an exponential sum. And I'm telling you that this sum exactly cancels, is exactly 0, unless this difference is very close to an integer vector.
And that's what the Poisson and smoothing is allowing us to see here.
Is allowing us to see very easily. There are other methods that will allow you to see the same thing qualitatively and quantitatively, but this is sort of the cleanest. Yes.
Yeah, I guess I was just wondering, like, what sort of we'll use Poisson here, I guess, is the other question.
Yeah. So it's to convert twisting by an additive character into translation of the Fourier transform, and that translation, together with the control on the transform, forces exact vanishing. It's amazing, right?
Yeah,
You have this this is an arbitrary smooth function with a couple of simple properties. And here's what the consequence is. Okay, so let's go all the way back here. So we have x to the delta. There's a factor of x squared that's come out. That's going to get hit with a 1/2. So in total, let me give this a name, star.
Right, because by going to y to z2, we lost, right, instead of x
Exactly.
to delta, we have x to 2. Right?
So now we have x to the delta from the original,
Exactly.
then an x squared from the Jacobian to the 1/2 is an x. Then I have a sum on a prime gamma 2 prime. This will be to the 1/2 still. So I have an a prime gamma 2 prime, and then the indicator function of two things. First of all, this thing, so A gamma 2 V is congruent to A prime gamma 2 prime V mod Q. That's one indicator. And the second indicator, since this thing is 0, the distance to the nearest integer is just this beta distance. And that needs to be within 1 over x. And the indicator function of, this is exactly what happened last time. We haven't done anything. Beta times, and beta is of size k over n. So let's simplify this a little bit. The distance between gamma 2v and gamma 2 prime v is at most 1 over x times beta, and beta is of size k over n. So this is, 1 over x times n over k, all to the 1/2.
That's how we're able to replace that inner like sum on y squared.
Yes. And so now we're going to break this into, so fixing gamma 2, okay, so there's a question here. So here's a little pop quiz. Do we want to fix gamma 2 and gamma 2 prime and get savings in A prime? Or do we want to fix A and A prime? So we're going to fix gamma 2. We're going to fix gamma 2 and we're going to fix A prime. We're going to fix gamma 2 and A. The question is, do we want to fix gamma 2 and catch A prime, or do we want to fix A prime and catch gamma 2 prime?
A prime, maybe we want to fix.
So once gamma 2 and gamma 2 prime are determined, and A is determined, then A prime is determined. That saves us Q. What I'm saying is, if we fix gamma 2 prime, then our only savings in Q is this A prime. And that's a savings of Q. It's completely determined. So it saved us a factor of Q. If instead we fix A prime, that determines gamma 2 prime mod Q. Gamma 2 prime V mod Q is determined. A prime is co-prime to Q, so I can move it to the other side. But that's a vector. That's a pair of vectors. So that's going to get us Q squared.
Okay. And it's like determined mod Q.
Well, from here.
Okay.
So if we fix A and A prime and gamma 2, then I sum on gamma 2 prime. Now, instead of summing on gamma 2 prime, I'll open this sum. Now I don't have to put absolute values. These are all indicator functions. Everything's not negative. I'll widen this to all vectors z prime in z2 in a ball of size y. And so now this is just z prime. Z prime has to be congruent to something mod q, and z prime has to be within y over k of a particular vector.
Okay.
Yep, so it's exactly what we did last time. So how many elements are there in a ball in R2 in Z2 of size y over k about some fixed vector?
N over x a squared.
Exactly. Exactly. X over, so n over x is y. So this is y over k squared, but I only get to choose one out of q squared of them. So there's a 1 over q squared, and then there's a plus 1, of course. Exactly right. Again, y squared is n to the half. But now we have k. Okay, so let's leave this plus 1. How many points do I have here? I have y to the 2 delta values of gamma 2. And how many points for a and a prime? Q squared. Okay, so all this to the 1/2. What have we learned in the end? So let's move the y squared in the q squared inside here. And now let's do the 1/2. So everything is bounded by x to the delta times x times a y to the delta times, now I'm taking square roots. So this is y over k plus Q. Bless you.
Both, but quickly.
Okay.
We want to do this.
Yep.
We're doing what, like L2 to L1 norm or?
Yeah, just in terms of big O. Yep,
Yeah.
exactly right. So what is this in the end? What have we saved? So I have an n to the delta. Remember what we need. We need to have something that just has where was it? Need to save Q squared. Need to save Q.
Yeah, one less, okay.
Yeah, so this thing, the trivial bound is Q times n to the 2 delta. We need something that's just n to the 2 delta and a little bit less. Okay, let me record that here. Need n to the 2 delta and then like Q to a negative power.
Right, so here, since you're already to the 1/2, it's not like the Q to the -2 that we need anymore. Right, we went through the.
It's not a Q to the -2.
Above you said, oh, because we're doing, was it Cauchy-Schwarz?
Yes,
You needed to save twice as much.
yes,
But now we're done with that part.
because we took the square roots.
Exactly,
Okay,
that's
yep.
what I meant.
And by the way, very good. Thank you for reminding me. We did save Q squared, but only Q squared. So watch what's going to happen. So here, let me write this as, let me pull this y outside and put a 1/y. And let me pull this q outside here and put a 1/q.
Okay, so this is n to the delta plus 1.
Yes, which is almost n to the 2 delta. N to the delta plus 1 is n to the 2 delta times 1 minus delta. Yeah.
Yeah, that's true.
Okay, times this q. And then what have we saved? We've saved a 1/qk and we've saved a 1/y.
Why was square root of n? Maybe I'm mistaken.
Yes, y was square root of n.
Okay.
Um,
And q was n to a small power.
and q was n to a small power.
I mean, I guess we don't have to say q because we have our expectations.
Yeah, look at this.
We're in the case of
We're in the case of k
case small.
small. So this is bad.
Hmm. Because K is gonna make that big.
Well, we have q over q. We've saved q, but not enough. What we've saved more is in k, but k is small. So this is not enough, just not enough. Just not enough, because I don't get anything else in, I'm missing this. I saved q. I need to save q and a little bit more, and that little bit more needs to be in q, because that's the variable that's large.
Oh, because we're doing this big O, we're doing in N. Then you're saying Q.
So we have an n to the 2 delta. The trivial bound would have been just q times n to the 2 delta. So that's why I wrote it as n to the 2 delta times q times something. Alternatively, if you like, well, any number of these expressions. Here's the trivial bound. N to the 2 delta times q is the trivial bound. We've saved 1/q and then an extra k, and we've saved 1/y. 1/y is great. But 1/q times k, we need to save a little bit more than when you put this all the way back. Should we put it all the way back? No, you can see.
Fine, yeah.
Yeah. So we've saved in k, but k is small. That doesn't save anything. I need to save in q. We're in this little strip where k is small.
And then Q
Q is something. We need to save in q.
Maybe if you go to the triangle and you draw like a smaller diagonal, we could also deal with this, right? With an argument.
Yeah, if k is large, then so we've gotten a second bound for this region. But we already had that region. That doesn't help us.
No, I'm also trying to say that if Q is comparable to K. it
Sure.
also wins. So I guess, yeah, I'm just saying this,
Over here somewhere, yeah.
yeah, but also if you lower the diagonal.
But I don't want to go lower in the, I don't want
No,
to, yeah. Yep. Okay,
Q is large. Q being large. Oh, okay,
Q being
so
large is this
we're
this
not-
axis.
We're not exploiting that. is what you're saying.
Exactly. We have not made use of the fact that Q is large. We could make use of the fact that K is large, but that's not the region that we're worried about.
Yeah, so if a K is small, and so that's gonna give us a abysmal savings.
Exactly.
Okay, I see. So, and then what you did was like basically the same thing as yesterday.
Same thing as last class. Now we're going to do something different. I really hope we're going to have time to do this. So it takes a minute to do this argument because it's really going to introduce some new ideas. Okay, so now we're going to the second refinement. So the first refinement didn't get us anywhere, but it got us the same thing as the zeroth refinement.
So would you say what Kloosterman did is the first refinement
Yes.
and what Bill did is the
Ha.
second?
Yeah.
Because he got
I-
cancellation in the model.
In both A and in just the modulus or A and the modulus?
I don't know for sure,
I'm trying to remember.
but I imagine it would be both, but
So you can fix A on the outside and get cancellation on the modulus, and that's still a kind of first refinement.
yeah.
And then a second refinement is to, yeah. So let's try to do the second refinement. So second refinement. So I have a sum over Q of size Q and a sum over A co-prime to Q of the absolute value of R. Now I'll immediately remove the absolute value, Rn hat theta, and put a zeta sub AQ, which catches the sign. Okay, and I'll also immediately remove the Rn theta Q and put a sum over gamma 1 of size X and gamma 2 of size Y, e to the 2 pi I theta, V, gamma 1, gamma 2, V.
The R hat replacement.
The R hat, yeah, the new R hat. Okay, Cauchy-Schwarz in this variable so that we get both A and Q involved. What do we, is it useful for you guys to see what we need to save? That little bit of, what do we need? Okay, so again, I have an integral over beta of size K over N. And now I have the sup bound, the sup over R hat N, which we already had. And then this second refinement, a sum over Q and a sum over A of R hat. Okay, so this we already said is N to the 2 delta over K Q. That's from the zeroth Kloosterman refinement. That's the L infinity bound. The length of this integral is K over N. The trivial bound for this is Q squared N to the 2 delta. So these K's are already okay. The N to the 2 delta is there. I again need to save. So this Q cancels one of those Q's.
Yet another Q.
I
and
need
then some.
Q and a little bit more. So need to save, but now I have Q squared things to sum. Need to save, but it's going to be much more complicated, as you'll see. Q to the 1 plus a little bit. Okay, Cauchy-Schwarz. So I have a sum on gamma 1. I'll just write this as X to the delta. The sum on gamma 1 is replaced by a sum over Y in Z2, upsilon Y over X, and then a sum on A, first Q and Q prime of size Q, A mod Q, A prime mod Q prime, gamma 1, gamma 2 prime of e to the 2 pi I Y inner product theta gamma 2V minus theta prime gamma 2 prime V. It's a lot of syllables. It starts to become a syllable soup to the 1/2. Okay, but it's all the same. It's exactly the same as what we did before. Okay, Poisson summation in this. I think I don't even have to do it explicitly anymore. You guys are getting the hang of it. X to the delta, X comes out.
Wait, so you Cauchy-Schwarz like from all the way in the inside?
From
All
this
the way
variable.
outside. Okay.
So this is the variable that I Cauchy-Schwarz. Gamma 1 turned into a y with an upsilon thrown in, enlarging the sum.
Then you also have a Q and a Q prime.
Yes,
and
then
A
there's
and
some
A.
zetas.
Because everything else is squared.
Right, okay, yeah. So this is
I
like-
open the square and I reverse orders and I put absolute values. So I have a sum on Q, Q prime, A mod Q, A prime mod Q prime, gamma 2 prime, the indicator function of the nearest distance to the nearest integer of gamma 2 v minus theta prime gamma 2 prime v being at most 1 over x.
by doing the same stuff.
Exactly the same analysis. Okay, here's the problem. What if we want to break this up into a modular piece? That's a over q gamma 2v minus a prime over q prime gamma 2 prime v will be equal to theta gamma 2v minus theta prime gamma 2 prime v minus beta. Now the betas are the same. The betas are the same. Gamma 2
We chose them?
minus gamma 2 prime v. Yes, I chose to do the refinement to fix beta and try to get cancellation
Hmm,
in the modular part, because that's where I have problems.
right, yeah, okay. I see.
Okay,
And
so
then
this
you
is
say,
all
like,
fixed beta.
To do any better, then you have to deal with varying betas.
Exactly.
Okay.
Okay, so again, the distance to the nearest integer is bounded by all of these things. This is bounded by k over n times y. This is bounded by 1 over x. And so we get, this is bounded by basically k over x, exactly as before. On the other hand, what's the worst case of this?
I mean, the biggest can be like Q over 2 and Q, 1 over 2, right?
There's when q and q prime are co-prime to each other, this could be as bad as 1 over q times q prime. The denominator. When I put this number, what's the mesh of these things? The worst mesh is 1 over q prime. This is 1 over q squared. Q squared can be as large as 1 over n. Q gets as large as root. So this could be as small as, could be as small as 1 over n. And here I have k over x. There's no way I'm getting something out of this. So this is usually where the second refinement ends. You're screwed and there's no theorem. Okay. So here's where something really new is going to happen.
Wait, and again, why is it could be as small as 1 over n?
Well, because q is in a range.
Oh.
Q ranges up to root n.
I guess what I mean is like, why does this tell us that we're screwed?
So the way we argued before is that if this thing is non-zero, then it's at least something.
Oh, no,
But that
it's
something is small.
in this case.
Sorry, that something is too large to be bounded by the thing on the left.
It must be 0.
So it must be 0. We don't have that argument here. It looks like we're in trouble.
Wait, what happens if, I'm still,
Yeah,
I don't
so
think I'm
like
still
K-
seeing it.
K is gonna be, small.
K is small. Yeah, think of K as 1.
Right.
This is still 1 over x.
X is like root n.
Yeah.
Yep.
And on the other side, we're getting.
We're getting 1 over q squared, not 1 over q, but 1 over q squared because we freed the q and the q prime.
Yeah, it was 1 over n.
It,
Or sorry, 1 over root n.
it was 1 over q before, and q,
That can only happen at now.
well, no, it could happen. It could happen if q and q prime are on the diagonal. If q and q prime are the same, then the mesh isn't 1 over q prime, it's just 1 over q. So, but that's a small, and we'll see that cancellation.
I guess I'm just still not seeing the issue of like, okay, you're bounded from below by 1 over n. You're bounded by above by 1 over n to the 1/2.
Yes,
And there's a problem because,
there's no contradiction
Yeah.
with those two things.
oh, before what you're saying is that we were getting, oh, okay, I get it now. So you're saying
Before we had a
the
contradiction
to get the
That
zero.
forced this to be 0.
Oh,
now we don't have a
okay,
contradiction.
okay.
So there's no contradiction. Yeah, no contradiction. The problem is there's no contradiction. So that's, yeah, we want contradictions,
Yeah.
right? Contradictions put restrictions on us.
Right.
Okay, so here's the key idea. Next key idea is to make crucial use of the multidimensionality of this setting. We've been treating these just like they're integers, but they're integer vectors. Okay, so let's write, I need another variable, z to be gamma 2v. This is in z2, and z prime is gamma 2 prime. Okay, and let's write this as z1, z2, and this as z1 prime, z2 prime. These are not just any vectors, they're actually primitive vectors. Because gamma is in SL2z, these are actually coprime. So this GCD is equal to 1. Sorry, I'm abusing notation. I would take points off if a calculus student did this.
Parentheses,
Yeah.
GCD.
Let me put an arrow there.
They give you a proof of this, but don't look for it.
Sure. Okay, so the key idea is to let's look at each piece. So I have a z1 over q, which is going to be close to a prime over q prime z1 prime. I'm going to multiply this by z2 prime on both sides. I'm going to compare that to a over q z2 minus a prime over q prime z2 prime.
How did you come up with these quantities?
So I'm just looking at this. This is a over q z1 minus a prime over q prime z1
Oh, I see.
is small, and a over q z2 minus a prime over q prime z2 is small.
Z, right? Minus.
Yes, z, but z is a vector. So I'm just looking at the components.
You're looking at the components, yeah.
What does it mean that the integer vector is close? It's that each component is close.
Yeah. Okay. I see.
Okay, so I'm looking at a over q, a z1 over q, and a prime over q prime z1 prime. And I'm going to multiply both of these by z2 prime. I'm going to multiply both of these by z1 prime.
And you're multiplying them, why?
You'll see in a second. Okay, and then I'm going to subtract one from the other. And then we only have q's. And then we only have q's. Observe that this is equal to, this is common, and subtract it off. So it's only a over q times what I'll call curly z. Curly z is the determinant of z1, z2, z1 prime, z2 prime. It's just, there's nothing fancy about this. It's just a way of writing this. z1 prime, z2. Let's look at the distance to the nearest integer of this.
And this is going to give us a bound for the components.
You'll see. Yep. Well, it won't be for the components. It'll be for this. It'll give us something about this.
Something about that.
Yeah.
And that's going to be useful.
Yes.
Okay.
So these things are related. Let's continue the analysis here. These things are bounded by, well, there's just a z2 that got multiplied, z2 prime, I guess, got multiplied in times theta z1 minus theta prime z1 prime plus beta, the same z2 prime times beta z1 minus beta z1 prime. I'm just turning this first thing into the two components and pulling out the fact that I multiplied by zeta 2 prime. And then the same thing over here. Z1 prime times this theta Z2 minus theta prime Z2 prime plus Z1 prime beta times Z2 minus Z2 prime. Okay, what is this bounded by? This is bounded by 1 over x. This is bounded by y. So I get y over x. It was 1.
I mean, we said x and y.
We,
Square root of n.
we did say that.
Okay, we definitely want x times y to be n.
We definitely want x times y to be n.
And then we love some flexibility, but we said it's probably square root.
But in what proportion?
You'll see. So this is again a y. Beta is k over n. K over n. And z1 minus z2 is another y.
So now it's not so symmetric.
It's not so symmetric anymore. It's not so symmetric anymore. What we have, now this, if non-zero, let's continue our analysis. If non-zero, then it's at least 1 over q, which is of size 1 over big Q.
I mean, this is determinant.
Whatever it is, it's an integer.
Right.
This is now an integer.
Some integer. Okay.
So if the distance to the nearest integer isn't 0, then it's at least 1 over q. Now, let's look here. We have this y squared over nk and a y over x. And we want something that could be as small, this could be as small as n to the 1/2. In fact, we can do a little bit better here because remember that k times q is at most n to the 1/2. So 1 over q is at least k over n to the 1/2. I have a k here. What if y squared over n was n to the 1/2?
Y squared over n equals what?
The k, I see a k here.
Yeah.
So if this number, you see, we have a lower bound.
Mhm.
But if we had an upper bound that was also this order, that would be a contradiction. And that would force this to be 0. And I see a k sitting here. So what if we made y squared over n equal to 1 over root n? I.e., what if we made y equal to, this is n to the 1/4. So x would have to be n to the 3/4. Then this y over x would be n to the 1/4 over n to the 3/4. It would be 1 over root n.
Mhm.
And this would be k over root n. So again, this would be bounded by just k over root n. And it'd be at least 1 over q. And that's exactly the range where we have a contradiction.
Make this actually good. I mean, I guess this is very technical. I'm being annoying, but you have to also play with the constant, right? Because the rate is.
There are also constants, and you have to play with the
You
constants.
have to, you have
Yes.
to say we can find constants for
Yes.
y and. for
Yes.
to make a-
And should I remind you how we do that?
You could also do epsilon.
You don't. It's simpler than epsilons. What you can do is when you go back to the very beginning,
It seems like you cannot do that because the rates are.
what you do is you chop this up. You chop gamma 1 is in some ball. You chop that ball into 1,000 pieces
Like you said,
or
like-
1,000 squared pieces to make the constant so that the distance between any gamma 1 and gamma 1 prime in that one ball is at most 1 over 1,000 times x. Okay, so you can play with these constants and make the constants right.
And then does the rest of the analysis fall through from the
No.
previous parts? Were these modified?
No, there's more to do.
So there's, I guess one thing maybe that's more to do is the condition for, when you said if this is non-zero, it's bigger than 1 over q. The condition that makes it non-zero is more complicated.
That's right.
It's like the vanishing of this determinant.
That's right. Mod q.
So you have to do something.
That's right. That's exactly right. But Sorry,
Is it
Nick?
true that y and x cannot depend on k?
Y and X cannot be changed. You're exactly, this is going back all the way to Nick's original question. We can't be playing fast and loose with the definition of Rn.
Okay,
We had one original definition, which got us a major arcs, which is just one ball. Now we have two balls
Right, right.
that we split as a half in order to get the first refinement. Now we're saying we have to split it as a quarter, 3/4.
Right.
Which is it?
Some sort of compromise needs to be had.
So we're going to change Rn again. Change Rn theta to what? How about a ball of size n to the 1/4, another ball of size n to the 1/4, and then a third ball of size n to the 1/2. And if you want to apply the first argument, you group these two and this. And if you want to apply the second argument, this second refinement, then you group this and these.
Oh my God. And doing that, then it goes through?
So then, in other words, when you apply Cauchy-Schwarz in the first time, you apply it on both of these variables together and glue them. Alternatively, you glue these two when you apply Cauchy-Schwarz the other time.
Genius.
Definition, so it's e to the 2 pi I.
Yes,
Gamma 1, gamma 2 v, comma, gamma 3.
gamma 1, gamma 2, gamma 3 v.
So, and you run, because you're just looking for like finding a positive proportion of integers, you just run the whole argument in this choice of Rn theta, right? You don't use other ones.
Nope.
or this other ones. You
Nope.
just need to get something, right? So
Yeah, and we don't want just positive, we want density 1.
density ones.
Yeah.
Yeah. that's-
To go all the way back to Nick's original question, we have to do the major arcs analysis on this.
Right.
But that's actually very easy to do. You fix all but one of the variables
Uh-huh.
and then run the major arcs argument on the last one.
Uh-huh. So, like if this was the paper or something, you would just write down this and.
And then just go for it.
Exactly. And you wouldn't know why this was,
People would suffer, yeah.
yeah, and people would suffer. Yes.
Or they would talk to you, I guess.
Well, we tried, you should, okay, you tell me, read the introduction. I tried to explain this in the introduction. In fact, what we have to do is much, much harder than this. The truth is that Rn theta looks more like a sum over gamma in a ball of size 1/2, and then a ball of 1/4, and then a ball of 1/8, and then a ball of 1/16,
Oh,
and
boy.
so on. And there's log of these balls all the way down to constant size. And there's log of them. But when you multiply log many matrices together, there's all kinds of other problems.
No.
If you multiply a bounded number of times, things, the size of the entries are a bounded multiple of the size of the matrices themselves. It's just how many times you need to,
The exponent was not to 1,
yes.
so how many?
How many until you get down to n to the 1 over n?
It's not log.
It doesn't even matter if it were log. It's some n to the epsilon, but I think it actually is
This
Yeah.
you have to do the analysis on.
n to the 1 over log n
Yeah.
is 1.
Wait, and why did you need to break down these sums many times? Why did this end up being the truth?
Okay. Because I'm lying to you about what we did here. The major arcs were actually not powers. They were much smaller. So we had to be able to handle all powers.
So,
And
So that's why you get like these.
yes,
broken
so
up.
there was a whole cascade where you would zoom in on you would do all of your analysis, like you would keep all of these variables fixed and all of these variables fixed, and you would do your n to the 1/2, n to the 1/4 decomposition like this and like this in some intermediate range for every possible intermediate range.
It's like this picture is in your head, right? And then it's in your head, and then like someone who's reading this is not gonna know you have exactly this picture.
The hope is to write it in a way that if someone really wants to work through the details, they're all there. But how to find this is That's what we're doing here is the discussion. I think okay. I mean,
Spreading the knowledge.
Okay, so let's just summarize, since we're gonna obviously run out of time and we'll need next time to finish the analysis. Just to summarize, this is the new Rn. Rn theta is this, which we can break up into something that looks like an n to the half ball and an n to the half ball to do one analysis, but we can also break it up as an n to the quarter ball and an n to the 3/4 ball to do what we're doing now. When we break it this way, so this is the variable in which we Cauchy-Schwarz. Actually, the 3/4 is the one that we Cauchy-Schwarz, and the y is the short variable. Y is the short variable. X is the long variable. Then what we get is z. So this z, this determinant, z1, z2, z1 prime, z2 prime.
You're gluing matrices.
Yeah, oh God, yes. And some kind of, yeah, I wouldn't think of it that way. I just think of it as a technical device. It's congruent to 0 mod q, but it's also congruent to 0 mod q prime.
Yeah.
There's nothing special about it. It's also and congruent to 0 mod q prime. So it's congruent to 0 mod their, yes, well, mod their LCM.
Oh, but in this case, they're not relatively.
I don't know anything about them. It depends.
Oh. Okay.
Maybe they're co-prime, maybe they're not. Okay, so where we will pick up next time, gosh, well, we'll pick up right about here next time. So we have that the second refinement, so this sum over Q, a sum over A co-prime to Q, absolute value of Rn hat, squared or not, let's say not squared, is bounded by, we have an x to the delta times x times a sum over Q and Q prime and A prime and these z's, Z1, Z and Z prime, which are the substitutes. Z is gamma 2 V and Z prime is gamma 2 prime V. And then this indicator function that their determinant Z is congruent to 0 mod the LCM. And we still have all of these. We'll continue making use of these conditions that theta Z minus theta prime Z prime is less than 1 over X. We'll continue working on this. And this is all to the 1/2. So then we have a little bit more work to do to get the requisite cancellation. And we need Q and a little bit more. So now we need Q squared and a little bit more.